with the theory, if the Wronskian 0, then linearly dependent. If Wronskian not 0, then linearly independent. Now we move on to third order. You must remember, this is just to show only, show that the set of solutions y1, y2, y3 is linearly dependent. Linearly dependent. That means you refer to the theory. Theory says linearly dependent, the Wronskian must be 0. So how to form the Wronskian? This is the matrix. So you have 3 by 3 matrix because these are the 3 solutions. Third order, y1, y2, y3. First row. Second row, y1 dash, y2 dash, y3 dash. Third row, y1 double dash, y2 double dash. This one is y3, missing. Just fill up y3 double dash. This is second derivative. First row, you just copy from here, put it here. This fella goes here, and this one goes here, and this one comes here. So you have first row, fill up x, y1, y2, x squared, y3, 4x minus 3x squared. Now, y1 dash, you must know how to differentiate. Differentiate x respect to x, 1. Differentiate x squared respect to x, 2x. Differentiate 4x respect to x, 4. Differentiate minus 3x squared respect to x, minus 6x. And y1 double dash, differentiate 1, 0. Differentiate 2x, 2. Differentiate 4, 0. Differentiate minus 6x, minus 6. You must get this matrix. Don't worry about the solution. You just use the definition and the theorem. Now, determinant of this matrix, there are many ways to find. You can use the row operation, or you can use the column operation. So in this case, they use first column, determinant 3 by 3 matrix. So if you use any method, the answer must be 0. Then you say linearly dependent. This one is the correct answer. So you can find the determinant in any way. And there are many ways to find. So this is one way to justify the answer. So they select the first column. So x, first column, cancel first row. Then you have 2x, 4 minus 6x, 2 minus 6. This is 2 by 2 matrix. And the symbol in front of x is positive, and here is minus 1. This is minus 1. Cancel first column, second row, remaining element x squared, 4x minus 3x squared, 2 and minus 6. This matrix. And then the last one, plus 0. Because this is plus minus plus. You must know this symbol, plus 0 here. So cancel first column, last row, x squared, 4x minus 3x squared, 2x minus 4x. Now, you find the determinant of this matrix, 2 by 2 matrix. So 2x multiply minus 6 minus 12x, minus 4 minus 6x multiply 2, minus 8, minus minus plus 12x. And this one, minus 6x squared, minus 8x, minus minus positive 6x squared. This one is 0. So 0 all is 0. So you simplify this, minus this one, minus 12x, 12x cancel off. This is minus 6x, this is 6x cancel off. This one is plus 8x, this one minus 8x, 0. So the answer 0 is correct. 0 is correct. Therefore, the set of function is linearly dependent. Linearly dependent according to the theory. Now, this is example 3, but no answer given. Example 4, Both are, we can call it these two exercises. So you go home and try. Determine whether the function linearly independent or not. So you have two answers, either independent or dependent. Using the Wronskian 3 by 3 matrix, you must be very good at the algebra, the matrices, finding determinant, as well as you must be very good at calculus. These are the backbone of this for engineering mathematics 2, because you must know the derivative of constant, derivative of exponent, derivative of logarithmic, derivative of trigonometric function, as well as derivative for the hyperbolic function like sin, cos, and tang. Now, example 4 also determine. This is not solving, class. This is just to determine whether linearly independent or not. So you just have to refer to the theorem and then you solve. So these are the exercises for you. Just follow the example 15, slide number 15, example 2. Example 2 is sufficient because this is 3 by 3 matrix. Now we move on to homogeneous differential equation. Homogeneous differential equation. And the next one is non-homogeneous differential equation. We generally formed nth order. Nth order. The form is very important, plus nth order. N is this one, this part, an, dnx. This is nth order. But our focus is maximum third order, minimum second order. First order we already finished in chapter 1, so that is already over. Now our focus is on second order, then at most we can go up to third order. Of course, fourth order you can study on your own. So this differential equation, you see the right hand side, in the beginning we wrote gx. In this case, the gx is 0, and that's why they put in circle. So anx dny dxn plus an minus 1x dn minus 1y dxn minus 1 plus a1x dy dx plus a naught xy equals 0 is called homogeneous differential equation. Actually, we call this as a linear homogeneous differential equations. Example, you see this example, this one, you see, this, in this case, your n is 2. So we call linear second order differential equation. So y double dash, this is, if n is 2, this is a2 d2y dx power 2. So the a2 is 2, and the a1 is 3, and the a naught is minus 5. This is called constant coefficient. Write down here, constant coefficient. Second order linear homogeneous constant coefficient differential equation. Very long name, but they skip the word constant coefficient. Constant coefficient means meaning these two. This is constant. This is constant 3 minus 5. These are the constant and equals to 0. 0 means homogeneous. So you have to what we call identify first. Homogeneous, second order, linear, constant, coefficient, ordinary differential equation. Very long name. But we just cut short, we just say homogeneous. But the order can be second order, third order, fourth order, fifth order, and so on. It depends on the model of the engineering problem or any scientific problems or financial economics, business, and so on. Now, non-homogeneous, you see the left hand side is same. Left hand side is same, but the right hand side is not zero. This is gx. So we at the moment just to identify homogeneous and non-homogeneous, not solving. Solving comes under the next section, and that is what we call methodology. Now, non-homogeneous nth order, the left hand side is the same, but the right hand side is gx, is a function of x only. So we call this non-homogeneous non-homogeneous nth order differential equation. But the example here is second order non-homogeneous differential equation, because the right hand side is your gx is x squared, this fellow. Gx is x squared. So we call this as second order non-homogeneous linear constant coefficient differential equation. 2y double dash plus 3y dash minus 5y equal to x squared. This is second order. So we are just to what we call identifying or familiarizing ourselves with the type of differential equation. So we are now very much concerned on two types, homogeneous and non-homogeneous. So this is very important. Fundamental set of solutions. A set of y1, y2, yn of a linearly independent. So we want linearly independent solution of an nth order homogeneous linear equation on an interval I said to be set of fundamental set of solutions. So you studied linearly independent, linearly dependent. But linearly independent is called fundamental set of solutions. This is what is required. So end of the day, when you solve the second order homogeneous, in this case homogeneous linear equation, the solution must be linearly independent. This must be very clearly understood, because this is very strong definition. If you find linearly dependent solution, it is considered unacceptable. It will be rejected. Because this information, piece of information, is a very fundamental, strong statement about the y1, y2 until yn. What is y1, y2, yn? These are the outputs. So of course, the output is very important for you. So since it's very important, therefore, the output must be linearly independent. But how to verify linearly independent? You use the Wronskian method. But don't forget this fundamental set of solutions. This is the definitions. So the general solution, homogeneous linear differential equation, we want to know the form. How do you write general solutions? So this is general solution. After that, we will move on to particular solutions. First, general solution for homogeneous linear differential equation. For the nth order homogeneous linear differential equation, there is a fundamental set of solutions on interval I. So let y1, y2 until yn be a fundamental set of solution of an nth order homogeneous linear differential equation on interval I. So the general solution of the DE in an interval I is written in this form. So y is the combination of y1, y2 until yn. So what is y1, y2, yn? It depends on the order of the differential equation. If first order, only y1. If second order, you have y1, y2. So you have to combine two, make it y. The final output is y. But the y1, y2 are the independent solution because it depends on the nth order. So if it is third order, you have y1, y2, y3. If it's fourth order, you have y1, y2, y3, y4. So you combine all, you make it as y. So what is y? Y is called general solution. But the C1, C2 until Cn, these are the arbitrary constant we have to find. How to find C1, C2 until Cn? This depends on the initial conditions. If second order, they will give you two initial conditions. If third order, you have three initial conditions. So you use the initial condition, you solve. This one we will do it in the next lecture. Because the C1, C2, you cannot just let it be like this. You already found Y1, Y2, Y3, Y4, and so on. But the C1, C2 also equally important. But it comes after you find Y1, Y2. This you have to follow the steps. Step 1, step 2, step 3, step 4, step 5, and so on. So it will be very lengthy, but it can be solved. So we just do first for the homogeneous, and then later on we can move on to non-homogeneous. So this one, so the general solution of non-homogeneous, this is very important. This is the theorem, very strong theorem. Try to understand, try to catch the idea first, yeah? We are not solving, and we cannot come back to this part later, but you can refer. But if you already knew, then very easy to move on very fast after you study the methodology. So still we are in general solution, but we are now in non-homogeneous differential equation. So still we have y1, y2, yn be a fundamental set of solution associated, and the word is associated homogeneous linear differential equation. For the non-homogeneous, still you have to solve the homogeneous part. You see, this part is still same. There are two parts. One part is called, this is for the homogeneous differential equation solution. That is C1, Y1, C2, Y2 until Cn, Y, and X. And this one we call it as a Y subscript C. Write down, yeah? Y subscript C. Stand for complementary solution, YC. But they didn't write, yeah? As you know, this is for the homogeneous part. That means you don't consider the GX. For the non-homogeneous part, you have YPX. This is called particular solution, YPX. This P stands for particular solution. This P, this C stands for complementary solution. So your Y is YC plus YP. So any solution YP free of arbitrary parameters that satisfy the differential equation is said to be particular solution. This is the most difficult part, yeah? But we will do this later. This is called particular solution. But what we are trying to say is the non-homogeneous solution, the output, the Y, consists of two parts. So you have YC, that is, you solve the homogeneous part. For the inhomogeneous part, you have to use different methods. There are two methods to handle the homogeneous part and the non-homogeneous part. The homogeneous part is the differential equation, the left-hand side. The non-homogeneous part is the GX. But still, we will use the differential equation and then solve for the particular solution. After that, you combine both and then you give the final output. After you give the final output, still it will be general form because the C1, C2 not yet solved. Therefore, you use the initial condition. After that, at the last stage, you solve completely, full solution with the C1, C2 until Cn. And finding Yp is the major challenge in this topic, because the non-homogeneous part is, of course, more important than homogeneous part, because the homogeneous part is basically what we say is very easy to solve, because you are concerned about the left hand side only without the GX. That is the homogeneous part. But non-homogeneous part is more complicated because you have the right hand side is not equal to 0. So what are the methods? That's why in the first slide you saw there are two methods at the bottom, the last one. That one you can use the method to solve. I will go back again, I will show you. But at the moment we already reached to the last slide. So the homogeneous differential equation, the Y is the output. See the slide 22 here. This is your answer, C1, Y1, C2, Y2 until Cn, Yn. This is your final solution for homogeneous differential equation. For non-homogeneous differential equation, your Y is like this. C1, Y1x, C2, Y2x, Cn, Ynx, and the last term is Ypx. This is called particular solution. So you can write Y equals to YC complementary solution plus, easy to remember, Yp. So this is the short form in order to find Y as a final output. So for the homogeneous and non-homogeneous, if you look at slide 3, so of course we will do homogeneous constant coefficient, this one, and then homogeneous Cauchy-Euler equation, and the method to find for the what we call non-homogeneous is these two method class. Just letting you know now, undetermined coefficient method and variation of parameter method. So these two methods, undetermined coefficient method, variation of parameter method, is to find the what we call Yp. This is to find your Yp. This will be in the next lecture. And this Euler, Cauchy-Euler is one form of homogeneous. These two are homogeneous. Okay. For the non-homogeneous, it's not written here, but 2.4, 2.5 is to tackle non-homogeneous. So any question, class? I'm very sorry for the delay because it takes a very long time to get the slide and then to let you see the slide, because there is some disturbance going on. But after some times, it is okay now. So any question, class? Any question, class? So there is a time delay here. So can you share the slide on WhatsApp for us? When? You just wait when? The slides